Hello, my name is Tim Cotton, and I am CEO of Novaphos, a company with technology to help make phosphate production more sustainable. Phosphates are essential for life. All animals and plants use phosphate in essential biological processes, and there is no possible substitute. Most of the food we grow and eat needs phosphate, as fertilizer or as animal feed. Where does it come from? In fact, almost all of it comes from mined phosphate rock. Like many industries, the phosphate sector is responding to calls for improved ESG measurement, reporting, and most important, performance. The inherent nature of the phosphate sector, relying on traditional extraction and processing of a limited natural resource, raises special ESG challenges. How can we use our limited phosphate resources most efficiently now and in the future? This presentation focuses on improving the sustainability of manufacturing phosphate products. And there are certainly other important opportunities to improve our use of phosphates, such as fertilizer application practices and avoided food waste, but we will not cover those here. So, phosphate rock is the essential starting point for all phosphate products, and there is phosphate rock in many regions of the world. There's no imminent shortage of phosphate rock. But let's not forget that phosphates are essential for life and with no substitute. That makes phosphate very different from crude oil, copper, or other commodities. In the long run, humanity will continue to need phosphate products, and we need to be responsible in how we consume phosphate rock today. This is not just a matter of legal and regulatory compliance. This is our obligation to future generations. Of course, phosphate rock is just the raw material for making phosphates. To be most useful, it must be transformed into phosphoric acid. This transformation is a chemical process. The dominant method used around the world for many decades is to react phosphate rock with sulfuric acid in the wet acid process. Well, the wet acid process requires high-quality phosphate rock to be effective, and that means a lot of phosphate rock deposits are not used. And it means a lot of phosphate, or P2O5, is lost in mine tailings as phosphate ore is beneficiated to meet the requirements of the wet acid process. And let's not forget that the wet acid process generates a lot of phosphogypsum waste, about 5 tons for each ton of phosphoric acid. Where does this waste phosphogypsum go? Well, much of it goes into waste disposal stacks. There are 25 of these in Florida alone, growing at about 50 tons a minute. Like many other industries, phosphate manufacturing is a linear process where wastes are neither recycled nor reused. Can we get more circular in the phosphate sector? Well, there are many definitions of a circular economy. The definition shown here gets at an essential concept. We need to design out waste. So where does waste come from in the phosphate sector? Well, we start with mined phosphate rock, which we then beneficiate to make the useful phosphate rock for the wet acid process. And this generates a lot of mine tailings that contain valuable P2O5. Then we add sulfuric acid, and that feeds the wet acid process, which does indeed make phosphoric acid, but it also makes a lot of phosphogypsum. So, for each ton of useful phosphate products, we get about 10 tons of solid wastes. What if we could reuse or even avoid these wastes? Well, with the Novaphos technology, we can use phosphate ore directly to make phosphoric acid. We can recover P2O5 from existing tailing streams to make phosphoric acid. We can stop producing waste phosphogypsum. We can even reprocess gypsum from existing wet acid plants into useful products. Here's the Novaphos process for making phosphoric acid. We start with low-grade phosphate rock, or even mine tailings. And this can be at 12 to 20% P2O5 and contain a lot of impurities. We add some silica if needed, although a lot of low-grade phosphates already contain enough silica. And then we add a source of carbon, which participates in the phosphate reduction reaction. We grind, dry, and agglomerate this feed material, which then goes into a rotary hearth furnace where the reduction reaction takes place. The resulting phosphate gas is absorbed in water to make a phosphoric acid, and the processed feed material exits the furnace as a useful solid calcium silicate product that we call JROCs. Here's the similar Novaphos process for reprocessing phosphogypsum. We combine phosphogypsum again with silica, but in this case there's no carbon. We grind, dry, and agglomerate the feed. And for phosphogypsum, which is less sensitive to certain operating conditions, we can use a straight grate furnace or similar system for the reduction reaction. Sulfur gases are captured, either as sulfuric acid or ammonium sulfate, and the depleted feed material is even more JROCs. So this slide shows you the essential chemical reactions taking place in each process. We won't spend a lot of time now reviewing these in detail, but they may be useful for understanding how the Novaphos technology works. So, what is a rotary hearth furnace, or RHF? This equipment is used widely in the direct reduction of iron ore, and there are about more than 100 RHFs operating around the world today. In an RHF, a turntable rotates through a circular tunnel, carrying the feed through different zones where temperatures and atmospheric conditions can be controlled. The phosphate exhaust gas is captured and passes to the hydrator to be absorbed in water to make phosphoric acid. Here's a picture of the Novaphos demonstration rotary hearth furnace. It's about 5 meters in diameter and can handle feed rates of up to about 300 kilograms per hour. We've operated this RHF with natural gas heating to date, but we do plan to add electrical heating in the next few months. And we've previously demonstrated in a smaller pilot RHF that electrical heating can be highly effective as an alternative to natural gas. Here's a large-scale RHF. These can be up to 70 meters in diameter with feed rates exceeding 1 million tons per annum. Of course, as I said, the Novaphos gypsum process can actually operate in a straight grate furnace. There are many of these in use around the world for many different applications, and feed rates in this equipment can be easily several millions of tons per annum. The Novaphos process produces high-quality phosphoric acid because many of the impurities in the phosphate rock stay in the JROC's solid products. We'll talk more about JROCs in a minute. The high quality of Novaphos phosphoric acid makes it suitable for more valuable phosphate products, like liquid fertilizers, animal feeds, or raw material for purified phosphoric acid. One exciting application for Novaphos technology is LFP, or lithium iron phosphate, which is becoming an important part of lithium-ion batteries for electrical vehicles and grid-scale storage. More than 90% of LFP is produced in China, and all of it comes from traditional phosphate production methods that have the very same sustainability issues we've talked about. Novaphos offers an opportunity to make LFP with sustainable phosphate inputs, made locally, from existing mine tailings, and without gypsum. JROCs are useful and safe. The calcium silicate structure of JROCs completely changes how impurities in phosphate rock behave, including radioactive impurities. This table shows that JROCs are non-toxic under US EPA T-CLIP standards. A lot of phosphate rock, and thus the products from that rock, contain radioactive impurities. The big question is whether or not those radioactive impurities become a public health risk. Well, this chart shows that radium exists in Florida phosphate rock, phosphogypsum, and in JROCs at levels higher than contained in native soils in Florida. But the real question should be exposure to radiation, for which radon gas emanation is critical. This second chart shows that radon emanation is indeed high in phosphogypsum, which is not surprising given that the wet acid process acidulates all impurities in phosphate rock, making them more mobile. But radon emanation in JROCs is very low, lower even than the radon emanation from native soil. In fact, it's as much as 50 times lower than radon emanation from phosphogypsum. Third-party lab studies and risk assessments have confirmed that the use of J-rocks in construction, for example, would have a negligible impact on radiation exposure to workers and the public. How can we use J-rocks? In fact, they represent a valuable ingredient in construction. They can act as an important substitute for cement and concrete, particularly where concrete durability is important. This is the case in Florida, which has many roads, bridges, and buildings susceptible to salt attack from ocean water. In this application, J-rocks can serve the same function as coal fly ash, which has been mandated by transportation authorities for these kinds of applications. With fewer coal-fired power plants, coal fly ash suitable for concrete continues to decrease and is now in short supply in many parts of the country. Similarly, J-rocks can serve as fine aggregate material in concrete, where the porosity and light weight of J-rocks can be valuable for internal curing and reducing structural weight. Finally, J-rocks can serve as a silicon fertilizer. Plant-available silicon is gaining recognition as an important micronutrient, and there are few economic sources of it. Instead of being a costly waste like gypsum, J-rocks are a useful and valuable product. Novaphos has been working with the University of North Carolina and other concrete experts to demonstrate that J-rocks perform well in concrete. These charts show some of the testing results, with concrete that includes J-rocks instead of coal fly ash, showing good set times and compressive strength. One goal of this testing program is to secure approval by Florida Department of Transportation and other authorities. The Novaphos process can use electricity to drive the essential reduction reactions, which means that it can use renewable energy. The carbon dioxide produced in the chemical reactions in the phosphoric acid process can be relatively pure, making it highly suitable for capture as an industrial gas or sequestration. And using J-rocks to displace cement and concrete means reducing cement production, a major source of CO2 emissions. So, yes, phosphate production can get more circular. Novaphos can reuse waste mine tailings to make phosphoric acid. Other outputs from this process are useful co-products that can be reused in other applications. And we can also regenerate sulfur-based products from phosphogypsum, while still eliminating waste and producing other useful products. We at Novaphos look forward to being a part of this transition. Thank you.